Good day, everyone, at this Tech at Lunch session of March. Today we will be talking about thousands of novel architectures in minutes to design more efficient thermal systems, which will be presented by Benjamin Mavot and Bart Peermans. During this session, you can ask your questions using the chat function, which will be addressed at the end of this session. You can also raise your hands, a virtual hand, and you can ask your questions using your microphone at the end of the session. So please don't hesitate to ask your questions. They are very welcome. Good to know. We will be recording this session and we will share it with you afterwards. So now I would like to give the floor to Benjamin. It's up to you, Benjamin.
Thanks for the introduction. Good day, everyone. So at first here now, we'll introduce the current way of working for a system engineer to design his product. So he normally in his current way of working, he starts with a set of components which system engineer has to select from and then start constructing a certain architecture. And this is manual work that will lead to a certain manually constructed architecture here and given in this example in series. As an alternative way, if he, for example, selects another component from his library and notices, from his own experience that a parallel architecture is better, he can come up with a different architecture, and then we have one in parallel. Of course, now he also wants to determine how good these designed architectures are, and his next step will be to simulate them in his the simulation framework of his choosing. And so from that, he will have a set of KPIs that are determined for every manually constructed architecture, and he can rank them himself. Now, as you may imagine, in these days, due to an increase in complexity of these systems that need to be designed, the problem gets more and more difficult. The set of library of components that need to be connected to each other increases, and furthermore, there are also a lot of alternative designs that need to be considered. And what also significantly complicates the situation even more is that there is a high level of integration between these components, and that has also the system engineer also needs to consider this. And third problem that we see is that customers demand that a certain design product is feasible for their specific case, and so the product that needs to be designed should be reconfigured or be optimal for a wide range of operations. And so this all needs to be considered during the design process. And as well known, the early design and decisions have a significant impact on the final cost of the product. And so it's at this stage that every alternative should be considered, and any effort spent here will be paid back later in the design process. And so what we have developed in this project and what we are going to present here is a tool to automatically generate these architectures to assist the system engineer when designing his architecture. It's we not only are going to generate them, but then of course also feed them to the next step, and that is simulate them. So what we have is though the automatic generations of thousands of or even more possible system architectures. And this is all just only based on a library of components provided by the system engineer and some user-defined high-level constraints on the architectural level of the product design. And so this will all be generated in a couple of minutes. So yeah, this goes very fast. So why do we want to do that? We want to accelerate the design exploration phase. But the second part that we want to optimize is that we also want to make sure that we have the most optimal design choice at this stage of the design process by having a very broad search. And so, as already mentioned, the choices made now will have a final big impact on the cost. So we don't want to, after going to the next phase of design, go back to the drawing table and look at the needs of another architecture. And so what are the typical use cases where the tool shines most out is if we look at systems which are, of course, consisting of different parts and where the sum of parts makes it possible to simulate your product, and where there is also a possibility to integrate your different parts in different manners, and where this has to be determined. Now let's look at how this is implemented itself and how it works in the flow of the user. So he starts with a certain component library as shown in the first slide. So this is a set of components that should be part of the architecture. Then he also has to specify the architecture itself. With that, we mean that he needs to select the components from the library which should be present in it. But furthermore, he can also maybe highlight the alternatives or the maximum number of certain components. But this will be demonstrated in a demo. Then the next step is for him to introduce a set of high-level constraints on the architecture itself. And these then are combined and sent into the tool we called topogen, which generates these thousands of topologies. Topology is just a sort of high-level form of the architecture. Now, with these architecture itself, of course, we need to go into a further step and design their KPIs, their efficiency or other qualities, and check which one are the best. And so for this, we go to the next step is toposim, which based on some model settings the designer defines. For example, the load of the product under design. And these are sent into toposim, which will determine the KPIs of every architecture. And based on this, the designer can pick the most interesting one and go into the next step of the design process. The next part is still work in progress. On the one hand, we have TopoOptim, where we want to look at how to make this generation phase more intelligent based on the TopoSim results. So if we look at the KPIs, we will detect certain architectures which perform very good. And so these are interesting designs that we should look more into and look at alternatives that look alike. On the other hand, we can also have certain architectures which will perform always very bad, and so we will try to exclude these in the generation phase. The next step that we have is a topo control. For example, if the user itself has multiple load cycles, different results may come out of or different optimal architectures may come out of TopoSim. And so there we can look for, in the case, for example, of thermal architectures, we can look into combining different optimal architectures into one with the use of valves or something like that. And so let's now look further at the step after TopoGen. So the generation itself, what does it look like? Here we see the components back from the first slide, and in a typical, like explained there in the way of working, the designer can come up with some designs himself. This can go from a simple serial architecture or a classical parallel one. He can even go further one step and then look at the hybrid one. And so what TopoGen does is it not only generates these architectures, but also looks at all possible alternatives. And to give you an impression, with only 4 components as seen here, we already go to 38 architectures, so 38 solutions. So if we increase even the number of components or possible alternative components, then this scales exponentially and the number of solutions increases very rapidly. So this is for the generation of the architectures. As mentioned in the invite, we will also talk about the application of it on the eEvoke use case, but for this I will give the word to my colleague Bart.
Yes, thank you very much, Benjamin. So what I will talk about next is our use case, which is a thermal problem based on our electrified Range Rover Evoque. And this electrified Range Rover Evoque is actually a research vehicle that we have already for over some years at Flanders Make. And it is an actual Range Rover Evoque, which has been electrified. So the combustion engines have been taken out, and we placed an electrical drivetrain in it, with in the front a dual motor, in the back a dual motor, and some inverters, a DC-DC converter, a battery pack, these kind of things, such that the entire vehicle is electrified. Now that means a dual motor in the front, a dual motor in the back. So that means we have 4 motors, and each motor can drive 1 wheel, so we have a 4-wheel drive. Now, what do these components need? They need cooling, and that's where our use case comes from. So we have components that need to be liquid cooled, like the motors, inverters, and the DC-DC converter. And on the other hand, we have also components which are air cooled, like the battery pack. Now, what we're interested in is how should a thermal architecture look like a cooling circuit for our use case. And what we actually want to do is we want to use a topology tooling to generate the best architectures, and that we also can compare it with the benchmark case. Speaking about the benchmark case, so how is the cooling circuit now done in the Range Rover Evoque? So we have a diagram on the right, which is already serving for some years, and that's actually a reference thermal architecture. From this picture, we created a benchmark model in Simscape, which is for us our simulation software. So that's the software that we use to evaluate all the architectures. What you see on the left bottom is the model for a 1-wheel drive use case. So we've simplified the use case for today to only 1-wheel drive. Now, what we see on the left bottom is already the benchmark. Then we go to the flow chart that Benjamin showed, and what's the next step? What we need to do is extract a component library out of this. So extracting a component library means that we extract all the components that we need in the topology generation tooling in order to generate these different architectures. We end up with an inverter, a DC-DC converter, the motor cooling methods, and these kind of things. And all these things can be fed into the topology generation tooling. What we should not forget is, of course, the constraints that Benjamin has been talking about. We will apply some constraints in the tooling, like we will tell the tooling we have, for example, a pump. Why? Because the tooling needs to know that the pump is some kind of pressure source for a thermal liquid cooling loop. What's also added is, for example, we want to have the inverter, the DC-DC converter, and also the motor inside of the topology. So we will put a constraint on it that they will all be embedded in all the architectures that are generated. These things are then put in the tooling, and the tooling will automatically generate all the architectures. And before we go to the full generation simulation and evaluation, I will quickly give the word back to Benjamin because he has some things prepared for a live demo.
At the risk of Murphy messing up, we will try to give a demo. So as you can see now, you see here the tooling itself live in action. So you have here where we first define our new computation where we will generate the different architectures. As mentioned, you can upload a certain component library, but this is now already in place here for us. Now the next step is to define the architecture specifications, so we determine which components should be present. So we, for example, add the fluids, add our cooling methods that needs to be included. And then also we add the pump as mentioned by Bart. So this is now our architecture specification. This is the input on the one hand. The next what we have is the high-level constraints. As you can see here, this is now a list of constraints. Of course, this is a work in progress and constraints will be added during the project. The first one we add is the pump. So this makes sure that every cooling method has a fluid to cool with. Then we can also determine on the fluid itself that there should be one in a circuit so that there is also a fluid present there. We can add the requirement of certain components so that they will be part of the architecture. And then we can also include other ones. For example, here we say that the fluid can have at most one connection, which is enough. Then here you see the solver where we can have different options. If we now pick, for example, the parallel one, we can specify the number of cores. This problem can be parallelized very well, and there is a small overhead cost, so it's ideally suited for this problem. So then we submit the problem. As seen here, it's submitted and it's listed in the computations. We already now have 40 generated architecture. We can refresh and now it's already done. We can go have a look at them. We can display them. So these are now architectures generated on the spot. And you can also send them into Simscape, so the TopoSim part, to evaluate them all. We see here that, for example, this is a hybrid one, a bit of series where there are two components in parallel. As you can see here, we can go to the end of it, and then in the final we have 219 as we started counting from 0. Architecture in total. In the end, while the simulation is running, the KPIs of every architecture will be displayed here in the table. We already prepared one where the simulations have run, and if we maybe first look at them, you can see that every topology has its associated KPI. And then we can, of course, also display this in a graph, and then we see something like this, where the different KPIs of every architecture is plotted, and from this Pareto front can be constructed. If we now maybe look back, if we have a bit of luck, then the first ones could be already, not yet. So here in the background now, the simulation is running and the KPIs will be entered here. And the designer can look back on a later point to check if the simulations have run. So now I give the word back to Bart, where he will talk more about the results.
Yes, let us quickly jump back to the presentation. So Benjamin showed it already, how the KPI plots look like. So what actually happens is you have the generation tool, the simulation tool, and the evaluation. It all goes automatically, and you end up with your predefined KPIs. That's something that you need to put in as a user, of course. You end up with a plot that you can make like this for a use case. What we see here on the left, we have a thermal index. On the y-axis, the thermal index is defined such that when the higher the index, the lower the temperatures of the components, so the better the cooling. And the same for the pumping power index on the x-axis. So the more you go to the right, the lower the pumping power. So that means that all the architectures that you see on the orange line, that these are the best ones. It's a combination of architectures. Why? Because other architectures have a better thermal index, so the lower pumping power, or vice versa. So you end up with a Pareto front. Now, out of these 219 architectures that were generated, we end up with 16 architectures on the Pareto front, and that only in like 4 minutes. 4 minutes needed for generating, simulating, and evaluating. And after this, a system engineer has 16 architectures that he can take down the line and further investigate and check what suits best for this application. It's like Benjamin just showed. There are like parallel connections, serial connections, and hybrid ones. In our use case, the serial connections are more located on the right because the flow rate does not need to be split up. You have slightly higher pressure drops, but the pump needs to work lower and you have reduced pumping power. But on the other hand, your thermal index is lower because each component is getting a fluid which is hotter and hotter. And that means that the component in the last at the last point in the series, it's getting the highest temperature. Whereas if you would have a parallel connection, it's just the other way around. You have more flow rate, more pumping power that you need to put in, so more operational cost, but the components itself are cooled better. And this is what a system engineer can take down the line to further investigate and match with their application. Now, of course, there is still future work. So we have shown now what's the status of our tooling, and our tooling is able to capture things on the fluid side. So cooling, thermal liquid parts, these kind of things. But if you look at other domains like the mechanical domain, electrical domain, there is not much of a difference with how these things need to be handled. And something that we want to do next is extend the tooling that's also compatible with these domains. In that sense, that it can capture all the features of Simscape, make it fully compatible. And even in the future, it could be that with other tools that we could link it, that it should not be specifically Simscape, but there are a lot of simulation tools which could also be linked to topology tooling. Something we should always keep in mind is intelligent constraining. What's this actually? We have an engineer, and this engineer needs to put his thoughts into the tooling. If you don't think enough and you don't put your experience into the tooling, it can generate all kinds of architecture. But if you do some intelligent constraining, you will be able to narrow down your problem to a much smaller one. Be able to condense the amount of architectures that are generated. It will be much quicker and will be much better for the engineer itself. So the brain of the engineer is still needed. And the last part is the integrated control and optimization. It's something we touched upon already earlier in our flow chart. The optimization part is where we would like to feed back the KPIs that are coming out of the simulation part to the generation part, that we can look into the design space in a clever way. So in the current tooling, we generate all architectures based on what's selected and the constraints, but we could do that. We could link this with optimization, that we don't have to generate all architectures, but we can look in a clever way in the design space. The topo control is still another thing where we want to combine architectures, including valves, and that if you have different operating regimes, that you can have the best of both worlds. But that's all work in progress. Quickly to wrap up, we demonstrated today a constraint-based architecture generation, which is also able to automate is to able to generate, simulate, and evaluate all architectures in an automated way. And we demonstrated for evoc thermal problem, where we demonstrated for a one-wheel case, and we were able to generate 219 architectures, simulate them in only 4 minutes. And we were able to get the best of all the architectures, which is a set of Pareto optimal configurations. We have our contact details below. So if you're interested, you can always contact us. And